A disaccharides upon hydrolysis gives two monosaccharide units, and these molecules are held together by glycosidic bond. The levo rotation of fructose is minus 92.4 degree, and it is more than dextro rotation of glucose, which is 52.5 degree only. The alpha form of glucose is obtained by crystallization from concentrated solution of glucose at 303 Kelvin, while beta form is obtained by crystallization of hot and saturated aqueous solution at 371 Kelvin. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 2 of the chapter Biomolecules. So in the last session we started with carbohydrates, right? As well as the different classification of carbohydrates. Discussed about the different methods of preparation of glucose, as well as we started off with understanding the structure of glucose, right? So the open structure we have already studied. So in today's session we are going to study about the cyclic structure of glucose, as well as we are moving on to the next one, that is next biomolecule, which is fructose. And then what are disaccharides? Under disaccharides we are going to study about maltose, lactose and polysaccharides. So all of this we are going to study in today's session. So let's begin with the cyclic structure of glucose. So already we have studied the open chain structure of glucose, right? There are 6 carbon atoms, there are 5 hydroxyl groups, there is an aldehyde group, there is a primary alcohol. All of this we have already discussed, right? But so there were few limitations of the open structure, because of which the cyclic structure of glucose came into existence. So let us see. Glucose does not give Schiff's test and does not react with sodium bisulfite and ammonia. So we have already discussed on the first carbon atom there is an aldehyde group. So if there is an aldehyde group present, it is supposed to show Schiff's test, as well as it should react with sodium bisulfite and ammonia if it is actually having a free aldehyde group. If an aldehyde group is present, it is supposed to show Schiff's test, but it is not showing. Okay, that means there is somewhere a problem with this aldehyde group. It means that the aldehyde group is actually not free there. It is present, an aldehyde group is present, but it is bonded with some other oxygen or carbon atom. It is not freely available. That is why the Schiff's test is not being answered. Now, glucose is found to exist in 2 different crystalline forms, which are named as alpha and beta. The alpha form of glucose is obtained by crystallization from concentrated solution of glucose at 303 Kelvin, while beta form is obtained by crystallization of hot and saturated aqueous solution at 371 Kelvin. So there are 2 forms existing, alpha and beta form of glucose. So we have already studied how to identify D and L, as well as what is plus and minus, that is dextro and levorotatory. Now there are 2 other forms, alpha and beta form, which was not being able to be explained using the open structure. So these were the few limitations, right? Because it was not showing Schiff's test, as well as alpha and beta form explanation was not given by that. So then we move on to the cyclic structure. This behavior could not be explained by the open chain structure of glucose. It was found that glucose forms a 6-membered ring in which the OH hydroxyl group at the C5, that means is the 5th carbon atom, is involved in ring formation. So this explains the absence of aldehyde group and also existence of glucose in 2 forms as shown below. So that we are going to discuss now. So what is happening? The aldehyde group which is present here, this is the open chain structure we have studied. So this is the aldehyde group which is present. So it is not going to exist because you can see the hydroxyl group which is present here on the 5th carbon atom. This hydroxyl group is going to involve in a ring formation with this first carbon atom, which is of the aldehyde. So you can see the structure here. This OH which was present here, the oxygen is now forming a bond with this carbon atom. So this is a ring structure. Now this is not an open structure and the aldehyde will be missing here. That means actually it is going to form a ring structure with the 5th hydroxyl group. I hope it is clear. So the aldehyde group is not free here. That is why the Schiff's test is not been answered by the glucose. So this is one form and this is the another form. So you can see here both of these are ring structures, but what is the difference here? Let's come back to the first carbon atom. You can see the hydroxyl group is on the right side, and on the first carbon here the hydroxyl group is on the left side. So based on checking your first carbon atom, if the hydroxyl group is on the right side, you can say it is the alpha form of glucose, and if the hydroxyl group of the first carbon atom is on the left side, you say that it is the beta form of glucose. And D plus is always a constant. D, how do we identify D? That is based on the lowest asymmetrical carbon atom you have to see. So you can see that the hydroxyl group is on the right side, right? It is on the right side, that is why it is D form. And here also it is the same. So that is why D form. And plus stands for dextrorotatory. Glucose is dextrorotatory. So I hope this is clear. This is how the ring structure of glucose is formed. Clear? That is the fifth carbon atom. In that the hydroxyl group is forming a bond with the first carbon atom. And how you can identify alpha and beta? That is based on the first carbon atom, not the last one, first carbon atom. This one will give you an idea about whether it is D or L. And this carbon atom will give you an idea about whether it is alpha or beta. Alpha if the hydroxyl group is on the right side, beta if OH is on the left side. Clear? So now moving on, these two forms that we have studied, that is alpha form and beta form of glucose, they are called as anomers. These two cyclic forms of glucose differ only in the configuration of the hydroxyl group at the C1 carbon atom, first carbon atom, right? And they are called as anomeric carbon. So this carbon, that's the first carbon atom, is called as the anomeric carbon. Rest everything is same, right? Rest all the structure is same. Only the first carbon atom, the position of hydroxyl group is differing. Based on that, you can say alpha and beta, and that carbon is called as anomeric carbon, and these two structures are called as anomers. They are called as what? Anomers. So how you can define anomers? Anomers will only differ in the position of the hydroxyl group in the C1 carbon atom. Clear? So such isomers are called as anomers, and the six-membered cyclic structure of glucose is called as Pirano structure. Okay, so why it is called Pirano structure is because the next structure that we are going to study is called as Haworth structure, which resembles pyran. Okay, pyran is a six-membered ring which is having an oxygen atom. Okay, so it resembles this one. This is also six-membered ring. 6 carbon atoms are present. Okay, and you have an oxygen atom in place of one carbon atom. So that is why it is called as a Pirano structure. I hope it is clear. So this was the ring structure, and from this you can write the alpha and beta form. Now another way of representing the structure of glucose is called as the Haworth structure. So this is based on the pyran structure. That is why it is called as Piranos. Now how do you write this? Okay, first you have to draw the basic diagram of this or basic structure of this, wherein you will put 2, 3. Okay. So like this, first you have to draw the basic structure of this. And now how do you place the hydrogen and hydroxyl groups or any other groups which is present is that this is the alpha form. So let's come back to the ring structure. So in here, how we are going to represent in the Haworth form is what I am going to tell you. So alpha form, how will you write this? Once you get the ring structure, whatever groups are present on the right side, you can see this is the structure, and you have hydroxyl, hydroxyl, hydrogen, hydroxyl on the right side. So all of that which is present on the right side, you have to mention those groups below. Right, that is below you have to mention. So you can see on the first carbon atom you have the hydroxyl group on the right side. So that will, see, this is your first carbon atom, that is mentioned here. Now on the second carbon atom also it is on the right side. So again you will mention it on the second carbon atom which is on the downside. Now moving on to the third one, hydrogen is on the right side. So you mention it here again on the downside. Right. So again on the fourth carbon atom you have hydroxyl which we are going to mention here. Fine. Now whatever is left behind, that is whatever is on the left side, that will come above. Clear? Right? So that is what is shown here. Hydrogen, hydrogen, hydroxyl, hydrogen. And the sixth carbon atom, you have the alcohol, primary alcohol, which you are going to write it on the top and the hydrogen will be below. So as simple as that. So the ring structure, once it is done, from that itself, you can write the Harvard structure. Whatever is present on the right side, you write it below. Whatever is present on the left side, you write it above. That's it. So let's write it down. You have HOH from the first carbon atom. OH below. So second carbon atom also you have OH below. So I'm going to write that. And on the third carbon atom you have OH on the top and H below. Fourth carbon atom again you have OH below and H. And on the last you have sixth carbon atom, which is your alcohol and the hydrogen atom. So this is the first carbon atom, second, third, fourth, fifth. And this is your sixth carbon atom. Clear? So this is how you mention. Now moving to the beta structure. So in beta structure you can see on the first carbon atom hydrogen is on the right side. So that is why this is the first carbon atom, hydrogen below. Then on the second carbon atom hydroxyl is on the right side. So that is shown here. Third carbon atom hydrogen will be below. Fourth carbon atom again you have hydroxyl which is below. Right. So whatever is in the left side you write it above and your sixth carbon atom will be mentioned here. So this is how you write the Harvard structure. I hope it is clear. So first you have to write the pyrene structure, 6 carbon atoms, and instead of 1 you will have an oxygen atom here. Then whatever is present on the right side that you are going to write down below. Whatever is present on the left side you are going to write it above. That's it. Clear? So this is how you have to draw the structure of ring structure as well as the Harvard structure of glucose. So that is alpha and beta structure. So you can see the difference here itself. On alpha you have hydrogen above and on beta you have the hydroxyl above. So from here also you can identify whether it is alpha and beta. Clear? Moving on to the next one, that is fructose. So we have completed glucose already. Moving on to the next one, that is fructose. Clear? So fructose, it is a ketohexose. Now, glucose was an aldohexose. That means it was having an aldehyde group and 6 carbon atoms. But fructose is ketohexose. That means the functional group present here is ketone. Right, that is why it is ketohexose, means again 6 carbon atoms are present. Clear? It is obtained along with glucose by the hydrolysis of sucrose. So, the preparation is the same as that we have studied for glucose. So, that is the hydrolysis of sucrose, C12H22O11, that is sucrose, C12H22O11 undergoes hydrolysis. That means addition of water in presence of an acid medium. What is it going to give? C6H12O6, that is glucose, and C6H12O6 itself, which is fructose. So that is the same method of preparation. Fructose also has the molecular formula C6H12O6, which is exactly the same as that of glucose. Molecular formula is the same. And has ketonic functional group. Which is the functional group here? It is ketone group at C2 carbon atom and has 6 carbon atoms in straight chain. It belongs to D series. So D series means the first asymmetrical carbon atom will have the hydroxyl group on the right side. And it is a levorotatory compound. That means it will be minus. Glucose was dextrorotatory. Fructose is levorotatory, and glucose and fructose is having D form. So let's see here on this is the first carbon atom, second carbon atom, third carbon atom, fourth, fifth and sixth carbon atom. Okay, again like in glucose all the 6 carbon atoms will be in the straight chain itself, and you can see on the second carbon atom you have the ketone. In glucose we have studied on the first carbon atom itself you are having the aldehyde group. Here on the second carbon atom you are having the ketone. Right, and you can see the lowest asymmetrical carbon atom will be the 5th one, and the hydroxyl group is on the right side. That is why it is a D form, right? And this negative sign stands for it is levorotatory. So this is the open structure of fructose. It is appropriately written as D minus fructose. Now D stands for hydroxyl group on the right side, right? And minus stands for levorotatory. Its open strain structure is as shown, discussed now. It also exists in 2 cyclic forms which are obtained by the addition of OH at the C5 to the ketonic group, that is the carbonyl group. The ring thus formed is a 5-membered ring and is named as furanose with analogy to the compound furan. So this is called as a furanose structure. Glucose was called as a pyranose structure because once it is forming a ring, it is a 6-membered ring, right? But here it is going to be a 5-membered ring because this hydroxyl group, that is the one we are discussing now. This hydroxyl group is going to form a ring with the second carbon atom. So in total you will have a 5-membered ring structure. But in case of glucose, this hydroxyl group was forming a bond with the first carbon atom. Clear? That is why it was a 6-membered ring. So that was similar to pyran. That is why it is called as pyrano structure. Here it is similar to furan. That is why it is called as furano structure. So here let's see the cyclic structure of fructose. So you can see here this is the first, second, third, fourth, fifth and sixth carbon atom. And you have the hydroxyl group on the right side. That is why it is D form and it is levorotatory. So now what is going to form in ring structure or the cyclic structure? This hydroxyl group is forming a bond with the second carbon atom, which is shown here. You can see the OH is forming a bond with the second carbon atom. And where is the first carbon atom? First carbon atom is mentioned here, CH2OH. So this particular group which is present here is mentioned here. So don't get confused with that, because we have to show the bond which is formed here. That is why the first carbon atom is written here. So this will be your first, second, third, fourth, fifth and sixth carbon atom. So again, like in glucose, fructose is also having alpha form and beta form. So again, how are you going to identify which is alpha form and beta form? So first let's discuss alpha form. So that is based on the first carbon atom again, right? So this will help you to identify D and L. So this will identify whether it is going to be alpha or beta. So you can see this carbon atom, first carbon atom, the hydroxyl group is on the right side. So that is why it is alpha form. Now here you can see, again this is the first carbon atom here. This is second, third, fourth, fifth and sixth carbon atom. Clear? So again the same way the fifth carbon atom and the second carbon atom is forming a bond here. So you can see here this carbon atom is having the hydroxyl group on the left side. That is why it is beta form of fructose. Clear? Now moving on to the Harvard structure of fructose. The same way how we have discussed for glucose also, we are going to do the same here. So the difference here is in glucose it was a pyrano structure. Here it is furano structure because only 5 carbon atoms. So again we are going to draw the base structure. That is this one. So first you are going to draw the furan structure, and based on the hydroxyl groups in hydrogen atoms, whether they are present on the right side or left side, like how we have discussed in glucose, we are going to draw that here. So let's take the alpha form here, hydroxyl group on the right side. So first we have mentioned that down, right? And on the other side you are having the alcohol CH2OH, which is mentioned on the top. Now moving on to the next one, on the third carbon atom, hydrogen is on the right side, so that is mentioned down. And on the fourth carbon atom, hydroxyl group on the right side, which is mentioned down. And in the last one, fifth carbon atom, you have the hydrogen atom on the left side. That is why it is mentioned on the top. And see, on the top. And the last one, sixth carbon atom, you have the CH2OH. So I hope it is clear. The same way we have to mention in fructose as well, how we have done in glucose. So the beta form, what is the difference here? You can see on the second carbon atom, you can see the difference. The hydroxyl group is shown below, and here the hydroxyl group is shown above. So from that itself, you can identify whether it is alpha or beta. So the same way we have done for glucose, whatever groups are present on the right side, we are going to write it below, and whatever groups are present on the left, we are going to write it above. So this is the Harvard structure of fructose. Now moving on to disaccharides. So till now we have been discussing monosaccharides, that is glucose and fructose. Now we are moving on to disaccharides. A disaccharides upon hydrolysis gives 2 monosaccharide units, and these molecules are held together by glycosidic bond. So that is also important to remember. In disaccharides, what is the type of bond which is present? It is glycosidic bond. It is called as glycosidic bond. So what is the speciality of disaccharides? Disaccharides on hydrolysis will give you 2 monosaccharide units. So one example we have already studied is sucrose. Sucrose is a disaccharide because it on hydrolysis gives you glucose and fructose. That is 2 monosaccharide units. Clear? Now glycosidic linkage, what it is? The linkage between 2 monosaccharide units through oxygen is called as glycosidic linkage. So you'll have two monosaccharide units and they will be forming a bond through or with the help of an oxygen atom. So that bond which is formed is called as a glycosidic bond or glycosidic linkage. So let us understand that. So the first one is sucrose that we are going to discuss, which is a disaccharide. It is a disaccharide. On hydrolysis, it gives equimolar mixture. So it is going to be equal amounts of D plus glucose and D minus fructose. So this D again stands for the first asymmetric carbon atom, hydroxyl on the right side. Okay, and plus stands for dextro. So D plus glucose and D minus fructose will be formed in equal proportion. These two monosaccharides are held together by a glycosidic linkage between the C1 of alpha glucose and C2 of beta fructose. So this is important to remember. So two monosaccharide units will be formed on hydrolysis of the sucrose, that is glucose and fructose. So the alpha form of glucose and the beta form of fructose. So the glycosidic linkage will be between the which carbon atoms? That is a C1 carbon atom of alpha glucose and C2 of beta fructose. So we are going to see the structure here. So sucrose on hydrolysis in presence of acid, what are you going to get? D plus glucose and D minus fructose. So it is the alpha form of glucose and beta form of fructose. So let us see the structure here. You can see this is the alpha D glucose which is present. We have already discussed how to identify alpha and beta. So this is the first carbon atom of the alpha D glucose. And this is your fructose. This is the second carbon atom. Okay, this is the second. This is the first carbon atom. This is the second carbon atom of beta D glucose. Okay, so you can see here the oxygen is forming a bond between these two carbon atoms. That is a C1 carbon atom of alpha glucose and C2 carbon atom of beta D fructose. So this is the structure of sucrose. Okay, so it is between C1 and C2. C1 of alpha glucose and C2 of beta fructose. Clear? Moving on. Sucrose is a non-reducing sugar since a reducing group of glucose and fructose are involved in glycosidic bond formation. So the functional group which is present, that is aldehyde as well as ketone, it is forming a ring structure, right? It is not freely available. That is why sucrose is a non-reducing sugar, because the functional groups, that is aldehyde and ketone, are not freely available. Sucrose is an invert sugar. Now why it is called as an invert sugar? Let's see. Sucrose is dextrorotatory. Okay, sucrose originally it is dextrorotatory. That means it rotates the plane polarized light towards the clockwise direction. But on hydrolysis, it gives dextrorotatory glucose and levorotatory fructose. We have already studied glucose is dextro and fructose is levorotatory. So sucrose is originally dextrorotatory, but on hydrolysis, it gives two products. That is, one is glucose which is dextro and fructose which is levo. Okay, the levo-rotation of fructose is minus 92.4 degree and it is more than dextro-rotation of glucose which is 52.5 degree only. Thus, the mixture is levo-rotatory. So, what is going to happen? Because glucose and fructose is formed and fructose is having more rotation or more degree of rotation, what is going to happen? The overall mixture is going to be levorotatory. Thus, hydrolysis of sucrose brings about a change in the sign of rotation from dextro to levo and the product is named as invert sugar. That is why it's called as invert sugar, because there is an inversion of the rotation of the plane polarized light. So what does that mean? Let's understand again. Sucrose, as discussed, sucrose is dextrorotatory originally. It is undergoing hydrolysis. It is going to form dextrorotatory glucose and levorotatory fructose. Okay, but what happens is initially it was dextrorotatory, but the extent of rotation is more in fructose, that is more towards the levo side or the left side. Because of that, this whole mixture, if levo rotation is more, means of course it is going to rotate more in the anti-clockwise direction, right? So overall the mixture is going to be levorotatory. So initially it was dextrorotatory and after hydrolysis it is going to be levorotatory. So because of that, initially it was plus and after hydrolysis it is minus. Because of that, there is an inversion in the rotation. That is why it is called as invert sugar. So this point is important to remember. Now moving on to the another disaccharide, that is maltose. So sucrose is done. Moving on to the next one, that is maltose. So it is composed of two alpha D plus glucose units. So it is forming or on hydrolysis it gives 2 units of glucose itself. So both of them will be alpha D glucose. C1 of one glucose is linked with C4 of another glucose. Okay. So where is this oxygen bond or glycosidic linkages bond is important to remember. Okay. So here in maltose 2 glucose units, both will be alpha only, and from C1 and C4 of another glucose. So the free aldehyde group can be produced at C1 of the second glucose in solution, and it shows reducing property. So it is a reducing sugar. So let's understand that as well. So you have the C1 carbon atom of one alpha D glucose, and you have this C4 of the another alpha D glucose, and you have a glycosidic linkage here. So 2 monosaccharide units are forming one glycosidic linkage, right? So 2 monosaccharide units, 1 glycosidic linkage. If there are 3 monosaccharide units, there will be 2 glycosidic linkage. So I hope that is also clear. So this is the glycosidic linkage which is formed between the C1 of one glucose and C4 of another glucose. Okay. So here the aldehyde group is going to be free. That is why it is also called as a reducing sugar, because it is freely available. Moving on to the next one, that is lactose. So this will be familiar to you. It is present in milk, right? So it is commonly known as milk sugar, and it is composed of beta D galactose and beta D glucose. So lactose on hydrolysis gives you galactose and glucose. Clear? Sucrose gives you glucose and fructose. Maltose gives you 2 units of glucose itself, and lactose gives you galactose and glucose. The linkage is between C1 of galactose and C4 of glucose. So this is the beta D structure of galactose. You can see here again, this is also a Pirano structure. Okay, so this is the beta D form of galactose, and the glycosidic linkage is between the first carbon atom of the beta D galactose, and this is beta D form of glucose, not alpha, beta form, okay, and which is between the C4. So C1 and C4, the linkage is present. Clear? Now moving on to polysaccharides. Okay, so polysaccharide contains a large number of monosaccharide units joined together by glycosidic linkage. So there will be more number of glycosidic linkages because more monosaccharide units are present. So first one is starch. Starch is the main storage polysaccharides of plants, and it's the most important dietary source of human beings also. So starch is important for human beings as well, right? It's a polymer of alpha glucose and consists of 2 components, that is amylose and amylopectin. Okay, so it is a polymer. Polymer means a large number of units of alpha glucose joins together to form starch, right? And it has 2 components. One is amylose and amylopectin. So let us understand about that. What is amylose? Amylose is water soluble. So this is important to remember. It is water soluble component which constitute about 15 to 20% of starch. This is also important. How much amount of starch is present in amylose and amylopectin? So the question can be differentiate between amylose and amylopectin, and it can come in the MCQ form as well. So it is important to remember. Chemically, amylose is a long unbranched chain with 200 to 1000 alpha D plus glucose units held together by C1 and C4 glycosidic linkage. Okay, so one glucose, the first glucose C1 carbon atom, and the second glucose C4 carbon atom will form a glycosidic linkage, and the C4 will form a bond with further C1 of the another glucose molecule. Clear? So moving on to amylopectin, it is insoluble in water. Amylose soluble in water, amylopectin is insoluble in water and constitute about 80 to 85% of starch. Here the starch content is more. It is a branch chain polymer of alpha D glucose units in which chain is formed between C1 C4 glycosidic linkage, whereas branching also is present in amylopectin, that is between C1 and C6 glycosidic linkage. Okay, so let's see the structure here. So you can see this is one glucose molecule, another glucose. Okay, so there is a bond between the first carbon atom and the fourth carbon atom using a glycosidic linkage. So this is a glycosidic linkage which is formed between 2 alpha forms of glucose. So this structure is called as your amylose. Clear? Now how is amylopectin formed? That is between the C1 carbon atom of one glucose and C6 carbon atom of another glucose. Okay, so this whole structure is your polysaccharide which is starch. That is, so this is amylose and this bond which is formed between the first and sixth carbon atom will give you another glycosidic linkage, and this whole structure will be the amylopectin. So together it is forming the polysaccharide which is starch. Clear? So let's understand the difference here. Long unbranched polymer of alpha D glucose. So you can see this much part is called as amylose. There is no branches which is present here, right? And long branched polymer of alpha D glucose is called as amylopectin. So once it is forming branches, this whole structure is called as amylopectin, right? Now it is water soluble. Amylopectin is water insoluble part of starch. It is having 15 to 20% of starch amylose, 80 to 85% of starch in amylopectin. Now monomers held together by C1 and C4 linkage. You can see here C1 C4 linkage in case of amylose, and monomers held by C1 and C4 linkage and branching in C1 and C6. So you have this linkage also as well as between C1 and C6. So this together is called as amylopectin. Two types of linkages will be there in amylopectin and only C1 C4 linkage in amylose. So in the next session we are going to discuss in detail about cellulose and the upcoming topics. So I hope the concepts that I have covered in this session is clear for you. So that's all for today. Thank you.